sodales nudite, vos quisitis dicite, mihi mesto partite, consulite per vostero tua pulcra facies me feblanti milies pectus abet glacies.
All right, so we left off last time trying to, or we outlined what we were going to do with add element for a linked list. And we outlined it and we made a couple of points, and that's where I want to pick it up at this point. The first thing we're going to do, like we did with our array-based list, is that we need to check the bounds, right? So if the index that you're trying to insert it at is negative, then obviously that's bad, and we don't want to allow that, right? Otherwise, if the index is greater than or equal to this dot size, then we will also throw an exception. Remember that it's okay if there are 5 elements in there, 0, 1, 2, 3, 4, those are all okay, but also 5 is okay because that's just inserting it at the end of the list, okay? So to check these bounds, we'll go ahead and throw new runtime exception, all right? And then I'll just say invalid index, okay? And of course we would want to check that. We've already gone through a JUnit test, a version of that for the array-based list. Next thing we need to do is find the node at which we want to insert the element. Let's come back to that one though. Then we want to create the new node, and that's just an easy constructor call. So a node of element of type T, remember that we already made this generic at the very beginning. We're accepting an element of type T here, and so we need to create that new node, and for lack of a better term here, I'll call it new node, right? Is equal to new node of the element of, and then also parameterize that, holding X, all right? Now remember this new node, this constructor that we're calling here, right? The element is assigned, but then the next is equal to null. So we know that that there's no next element there. Okay. All right. So now we need to make the previous node point to the new node and make the new node point to the next node. Again, the visualization here. Suppose that we were to insert 42, right? And we've created a new node here already containing 42, right? And it's pointing to null, or phi, which is our placeholder for null when we're illustrating this. Now suppose that we wanted to insert 42 at index equals 1. Well, first of all, we have to get there, right? So we're going to start at the head, as we always have to, then go to the next, and this is where I want to insert it. So what I'm going to do is I'm going to make the new node point to this node, and then I'm going to make the previous node here no longer point to that node, but to this new node, severing that connection right there, all right? And that's then you can imagine that you could pull this taut, right? That's why it's called a linked list, that it's all chained together. Once you pull this taut, then it's all one linked list there, all right? So I need to make the previous node point to the next node, and the current node, the new node, point to the next node. So let's go ahead and do the easy one first here. Make the new node point to the next node. So new node dot set next equal to the old node, which I haven't done that yet, but the next node, right? And I'll just leave that here as not real code because we're going to have to come back and fill that in, right? Did I do setters? Let's go ahead and check that out over here in the node, right? The node class. I've got getters now, right? And I preferred immutable objects, but I don't have a setter here. Now I have a reason to want a setter. So instead of typing it out, let's again go up to source, generate setters. I don't want to generate a setter for the element unless I have reason to do so later on. But I will definitely have reason now to have a setter for the next. And so I'll create that, and that's a way that you can update what it points to, okay? So we have a couple of things here to do. We have to make the new, previous node point to the new node, and we have to make the new node point to the next node, etc. What would we do at the end here? So before, in this example here, there are 3 elements to begin with. How many are there now once we've inserted 42? 4. So how do I keep track of that? This dot size plus plus, okay? All right, so get rid of that. That's all we really need to do. Let's come back up and now start filling in the difficult parts. First of all, we need to find the node at which we want to insert the element. Like I said over here, we would start at the head, right? Go off, there we go. We would start at the head, and I want to insert it at index 1 here, so I would have to traverse 1 to get that node right there, right? If we were inserting it at index 2 instead, then I would have to go next, next. How many times did I have to go next? 2, which is going to be equal to the index at which you want to be, right? Didn't we already do this? We did this on Monday, didn't we? We have another function here that we've already implemented, get element. How did we do it? We kept track of a current starting at the head, and then for with the traditional for loop here, for I equals 0 less than index, we traverse to the next node, updating the current equal to current dot get next until we arrived at the place that we wanted to be, right? And then we return the element there, right? So I'm going to go ahead and cut and paste this code here to get the current, the element at, or to get the node at a particular index. Now, before I cut and paste here, is cutting and pasting a good idea? Just cut and paste, that's okay? Is that a good design? Bad design. Anytime you find yourself doing that, rethink what you're doing, right? So if I'm going to use that code in this place and that place and maybe a couple of other places, what should I be doing with that chunk of code right there? I should be putting it into another function, right? All right. Public node t get node at index, right? Int index, int index. And of course, you would probably want to check the indices. We'll come back to that though. And here what I'm going to do is I'm going to return the current. I start at the head, right? And I traverse however many times you want, 1, 2, 3, to get to whatever you want. What if I traverse 0 times? I start at the head, and that's exactly where I want to be. I return that node right there, all right? All right, so before we continue here, however, is that a good design? Making it public. Should I allow access to the internal workings of my class, in particular that I'm representing the values in this list using a node? Should I expose that to the outside world? Probably not. We called that what? A leaky abstraction. Right? So let's make this private because I still want the functionality, but I want to make sure that the design is consistent with the object-oriented programming principles that we've covered. I want to make sure that encapsulation is preserved, the protection of my internal workings, right? Yeah, I'm going to call this in other functions, but I don't want the outside world to call this. Because if they did, then they could start mucking up with the internal workings of my class, right? So let's come back up here and refactor this a little bit. I don't need this. I'll call this the node, right? Is equal to this dot get node at index. There we go. And I will return node.getElement, right? Smaller code is generally better code, right? And repeated code is definitely wrong. It violates the DRY principle, the don't repeat yourself principle. All right, so let's come back up here. Now, find the node at which we want to insert the element. Well, there we go. And I'll call this node for now, right? And that's a call to the function that we just wrote, right? We create the new node, we make the previous node point to the next node, and then we make the next node point to this node. So in this case, I called it node, right? Maybe there's a better name for it. We'll come back to it later on, right? But now, how do I get to the previous? Right? So once again, over here, if I highlight this node right here, wait, right? If I highlight this node because that's where I want to insert it, is there a way to get to the previous node so that I can do these two shuffles here? Can I start at this node and go backwards in this linked list? No. So, but I've also got a function to do this for me, right? I need to get the previous node. Let me go ahead and make another call to get node at index. And instead of calling it node, I'll call it previous, right? And it's not going to be at index. What's one behind it? Index minus 1, right? So I've got the previous, I've got the node, which I'm now going to rename because I have a better name for it now. Next, right? And next. And this new node is going to be right between the previous and the next, right? So how do I make the previous node point to the new node? Well, previous dot set next equal to new node. Right there. All right. Now, before we continue, is it a good idea to make a function call twice right here? Let's think about this. Right? What it's doing is it's starting at the head and traversing a certain number of steps to get to where you want. And then it's doing the same thing again on line 20. It starts at the head and traverses the same path all the way up to wherever you're trying to get to. What if I have 1,000,000 nodes in here and I want to get to that 1,000,000th node to add it between the last one and the second to last one? This will end up doing how many traversals? 999,999, round that up to 1,000,000. How many traversals will this end up doing? 1,000,000. So 2,000,000 traversals, right? If there are 10,000,000 elements in there, then it would be 20,000,000 traversals. How could we cut that down? Do we really need to call this function more than once? If I've got the previous, can I just get to the next by going one more step? Instead of doing all that again, previous, yes, dot, get next, right? Now how many operations am I doing to get to the 1,000,000th element? Yeah, I'm doing 1,000,000 traversals up here, right? But then how many traversals am I doing down here? Just one more, right? So instead of 2,000,000 traversals, now I've cut it down in half to only 1,000,001 traversals or whatever. Okay? All right, that's great, right? It's still not perfect, but we'll come back to it. What I want to do is test it, right? You can do some ad hoc testing here. For example, you can go ahead and create my linked list and then add 1, 2, 3, 4 elements to it. But I want to do more formal unit tests over here. So let's go ahead and create another test. Test, public void, linked list, add element, elements, test. All right, there we go. All right, so I need a new linked list in this case. So my linked list. Actually, I should probably just call it list, but that's okay. It's just testing. And we'll go ahead and go with integers here. And I'll just call it list because that's all what it is. It's a linked list, right? And for integers. Now let's go ahead and add a couple of things to it. Let's go ahead and add element. Now we're adding it to the end. So let's go ahead and add 10. Then we'll add 20 and then 30, right? 20 and 30. Then I also want to test that add method with respect to an arbitrary index. So let's go ahead and go add elements, and then I forget what the order was. I think it's the index is last, so let's go ahead and go with 1. All right? So what should the list look like after this is all said and done? Obviously, 10, 20, and 30 are going to be in there. But if I'm inserting 10, or no, let's go with something different, 42, at index 1, what should it look like now? Should 42 be right here? Nope, that would be index 0. So 42 should be right here, okay? That's what the list should look like. How do we test that it looks like that? What we need to do is we need to pull out the values, right? Actual, and then int, let me go ahead and put them all in the same line, actual expected, okay? So what we're going to do is we're going to check that first element. The actual will be equal to the list.get element at 0, right? And then the expected is going to be, well, what would we expect at index 0? 10. Now we need to assert that those two things are equal. And for that, I'm going to just grab this code right here, right? And we want to make sure that the first element is indeed 10. Then we can do that for the rest by simply copy and pasting. Copy, paste, copy, paste, copy, paste. Right? Don't want to do that in general, but here we go. 42, and I would get the second element, then the third element, third element, then the fourth element. And each one of those should be 10, 42, 20, and 30, okay? Let me run these tests now and see if this works. Come on. There we go. And our linked list tests are failing here, right? And what's the reason? Let's come over here and examine this. And it's happening because there's a runtime exception, invalid index. So let's jump to where that's located. Oh, okay, you can't do that at line 16. Here we go. All right. So the bounds checking seems to be off here, right? Why? And in fact, where was this actually failing, right? The lists are not necessarily going to tell me, let's see, which test was this actually occurring on? It's actually occurring on the very first one, right? All I did to do that was I double clicked on it. So we have a corner case here to think about and to diagnose. When I start with an empty list on line 69, I need to add an element 10, and it immediately fails with a runtime exception. Why? Right? Well, we go to this this function right here. We add it x 10 to the size, right? And so we end up calling this function right here. And so if we start filling in the blanks here, that's going to take me to my interface. Let's go to the actual linked list here. I'm actually going to be inserting 10 at index 0. Okay. What is the current size? Because it's empty, right? So it's not negative, right? The index is not negative here, but the index is greater than or equal to size, right? So should we be throwing this exception? Undo, undo. What should it be here? Should be strictly greater than the size, all right? Why? Again, if you have 5 things in there, 0, 1, 2, 3, 4, those are all valid indices to be inserting at. But then also, index 5 is valid, right? So you want to make sure that it's strictly greater than that size. All right, let's see if that fixed it. And run this again. All right, so it still fails, but with a different type of failure, right? It fails with a null pointer exception, probably on the same line. Let's go back, line 70 here. All right, so it's failing on the same line, but it's failing in a different way, right? This is great because this means I'm testing well right here, right? What's happening here? I am adding an element to an initially empty list. We get to line 20 over in add element here. Right? In other words, the bounds check, that's okay. Getting the previous element, that seems to be okay. Getting the next one, that's where we end up with a null pointer exception down here. In other words, previous here ends up being null. Why does it end up being null here? Right? So once again, let's go ahead and think about what is actually input into this method. We're inserting 10 at index 0. Okay? Now let's come down here, and what node are we asking for then? We're asking for a node at index what? 0 minus 1. Oops, sorry. 0 minus 1. Is there going to be a node at negative 1? Nope. Right? So we've found the issue here, that when we're inserting at the very beginning of a list, right, or an empty list, then we probably have to think differently about this. Let's come back over to our whiteboarding over here. Okay. All right. So what does an initially empty list look like? Right? So what is the head pointing to in an initially empty list? Null. Right? Is there any node that we can insert, right? You know, like we've got this previous and this next, and we need to create this new one, and it looks like this. Right? There are no nodes here to do that with. This is what's called a corner case. This is what's called those extremal cases, where we probably need to handle this one a little bit differently. If I want to insert 42 into an initially empty list, I'm still going to be creating that node, and that's pointing to nothing right there. Right? But now, how do I insert it into the list? That ends up being my new head. Right? So instead of severing a connection from another node, I'm simply going to make sure that head is now pointing to this new node. So outlining that. One, I still create a node, create new node, right? But two, I don't shuffle a bunch of other references. I make the head point or refer to the new node. Right? And then I'm done. Oh no, I also increment my size. Right? So let's come back over here and let's go ahead and fix this now. Right? So this is a special case. So I'm going to go ahead and put this into an if statement. If this list is empty, then we need to insert the new element at the head. There we go. And that means that I'm going to create the node. I'm going to, so new node, node t new node equals new node of element x. And then I'm going to make this dot head equal to the new node. And then also size plus plus. Right? This dot size plus plus. Right? Otherwise, I'm going to do all of this stuff that we discussed before. Maybe it still works, maybe it doesn't. We still haven't figured that out yet, right? Because we've only started testing here, right? All right, now my first question is, this is not going to be the actual code here. How do I determine if the list is empty? How do I determine that? What's the size of an empty list? Zero. This dot size is equal to 0. Wait a second. That sounds eerily familiar, right? Let me come back over to my Java perspective over here. Actually, I'm already in the Java perspective. Let's come over here, right? My array list. Didn't we think that that was a nice thing to have? I think we called it is empty, right? Or maybe we didn't. Oh, okay, I guess we didn't, right? But maybe now we should, right? Let's go ahead and add a functionality here, right? Public Boolean is empty. Because that's way more English than saying equals a size of 0. The logic will be the same. Return this dot size equals to 0, right? If it's equal to 0, then it's true and it's empty. Otherwise, if it's not equal to 0, then it's false. Right? That sounds like it should be belong in both my array list and my linked list. So we're going to promote it up to my list. Right? And in fact, the actual implementation doesn't change. Right? Now both classes inherit this method. Right? I only have to write it once. And so over here in my linked list, I can change this code to if this list is empty. That's so much cleaner, right? So if it's empty, I create the new node, I set the head to this node, and then I increment the size. DRY principle, don't repeat yourself. This dot size is incremented here on line 23 and on line 35. Should that code be repeated? No. Let's go ahead and get rid of it. Where should it belong? Well, it happens in both cases. And if it happens in both cases, then it should happen outside of the if-else condition. Is there anything else here that we've repeated? I create a new node containing x, and I create a new node containing x. Where should that go? Should that be repeated? No. Let's go ahead and move it before the if-else condition. And now I don't need to have that line. I don't need to have that line. Okay? So cleaning up the code a little bit here. Right? All right, let's come back over here to my list tests and see if we now pass those tests. Okay. And looks like we passed everything. All right. Good enough? Ship it? Well, I want to test. What did we actually test here? We tested inserting 42 in the middle of the list because that's what we kind of designed it for, right? If we go back through this example explicitly is putting it somewhere in the middle of the list. Is there another thing that we should be thinking about here? Is there another extreme case? Let's go ahead and copy this, extreme elements test, add elements test at start. There, at start. There we go. So instead of adding it just in the middle of the list, 2 or 3 or whatever, let's add it at the beginning of the list. What should it look like then? 42 should be the first element now, right? All right, so we need to update all this stuff here. 42 should go here. The second one should be 10, and the third and the fourth one should be 20 and 30 as well. Right? Again, this is one of those corner cases. What happens when we insert it in the middle? What happens when we insert it at the beginning? What happens when we insert it at the end? That's also going to be one that we want to test. But before we test that, let's make sure that this one works, and probably won't. Right? Yep, it failed. Right? Now why? It failed at that location. It didn't throw an exception, so there's no problem with the index values, but it actually didn't get in as the first element there. Right? So what we can do is we can actually use our JUnit tests here as a debugger as well. So if you set a breakpoint here, you can come up to the debugging and run it. Hopefully that'll, otherwise we'll have to go back over to the demo. There we go. Let's go ahead and switch our perspective over here to the debug perspective. And let's walk through this. Why does it fail to get 42? Let's first examine the list here, okay? And this is actually a pretty cool thing that you can use with the debugger here. You can actually see the size is 4. 4 things got in there, so that's okay, right? Here's the head. What's at the actual head? Expand that, and you see that the element is 10. Right? Oh, okay. So 10 is still the first element. It's 10, 20, 30. I don't know what is it. Let's go ahead and check out the next element. Expand that and see that it's actually 42. That's weird, right? We, instead of getting 42, 10, 20, and 30, what we're actually getting is 10, 42, 20, and 30. Right? And if you check out the next one, you'll see that that's also correct, like I said, 20, and then the last one here is going to be 30. Right? So we've got another special case here. What happens if we try to insert at the head, but it's a not empty list? Right? Let's come over here and look at what it should look like. So if I've got 10 going to 20, going to 30, right? What I want to do is I want to insert 42 at the head. Right? Initially, if I create 42 here, right? Here's the head. Right? What I want to do is I want to make sure that 42 is now pointing to the old head. But what else do I want to do to make sure that the head is preserved here, the head reference? The head now should be pointing to 42. So there's another special case. The special case is going to be when you're inserting it at index 0. So let's go ahead and stop all this. Go back to my Java perspective. Right. There we go. Stop. There we go. And let's go back up to my linked list here. So maybe this is yet another special case. All right. So if you are inserting at index 0, right, then we will treat this as yet another case. There we go. Else. There. So how can I tell if I'm inserting at index 0? Well, if the index is 0. Right? Now, if this is the case, what are we going to do? Well, we're going to do what I just did over here. You're going to have to create the new node, which we've already done. We promoted that up to be for the if-else-if statements here. But I need to make that node point to the next node, and I need to make head point to this node. Right? So I'm going to steal some code here. Or not. What do I call it? New node dot set next to this dot head, right? And then I'm going to make the head point to this new node. This dot head is equal to new node. Do I need to increase the size here? In general, yeah, but where am I doing that? That's common to all 3 of these cases. So I don't want to do that here, otherwise I'd be increasing it by 2. Okay? All right. Does it work now? Let's go ahead and see our JUnit tests over here. Does inserting it at the start now work? It should. Yeah, it runs. But this is still not optimal here. I've got repeated code here and repeated code here, right? In fact, is empty, you're already inserting it at index 0, aren't you? Right? So if it's an empty list and you're inserting it at the end, where is the end? It's at index 0. This case and this case are actually the same, right? So could we collapse these? In other words, could I get rid of this first case here entirely? Let me go ahead and copy that just in case we need to restore it, right? Will this work for both cases? Let's walk through it and think about it first. All right, if it's an empty list, that means that head is null, right? And we want to insert it the new one, as the new head, right? So is there a problem with setting this to be null, right? The new node will point that, its next is going to point to null. There's no problem there at all. It's already what it's being pointed to, right? Undo, undo. And then this was common to both of them, so we're good. In fact, I can run our test cases here, and after that refactoring to make it a little bit more efficient, right? Because now we only have one corner case to really worry about. All of the tests still run, and all of them still pass, right? This is why you write JUnit tests, and why you want good code coverage, and why you want to consider corner cases and stuff like that. Because when you go back and you change something, you want to make sure that everything still passes. Well, if you tested it ad hoc like we were doing in, say, demo, right, then you're going to have to go through and do all that manual work again, okay? One more test case here. Let me go, not this one. Where's my list test? There we go. All right, I'm going to grab this, and instead of inserting it at the start, what's the other extreme case? What's the other corner case that we should test? At where? End, right? So we'll insert 10, 20, 30, 40, but now we'll insert 42 at the end, which would be, there are 3 elements in there, so 0, 1, 2, 3, 3. And we would expect it to look like this now. Instead of 42 being at the beginning, it should be 10, 20, 30, 42. Let's go ahead and change that back to 10, 20, 30, and 42 now at the end, all right? And let's run that one more time, and I've got 8 test cases now, and they all should still pass. Yeah, I don't need to consider another corner case at the end because it still works, right? All right, great. We have now implemented and tested CR, right? That is a way to create stuff, put stuff in, and a way to retrieve stuff, take stuff out. What else do we need to do now? This is the easy stuff. Or some of this is the easy stuff, right? Update element, right? So given an element X, right? We want to go to the node at index at the given index, and then we want to take the thing out of there and return it, and then we'll replace it with X because we're updating elements, we're replacing elements. Okay. What is my very first step here? Let's outline it again. What's the first step that we've been doing with all of these? Index bounds check, right? 2, or the second step, 1. Now what we need to do is we need to find the node at that index. Find the node at index, ... Sounds familiar, right? 2, replace the element and return the old element. So index bounds exceptions only allow them to ask for legitimate indices. If index is negative, or if the index is greater than or equal to this dot size. Now it is greater than or equal to because there are 5 things in there. 0, 1, 2, 3, 4 is valid, but 5 is not valid. I will throw new runtime exception invalid index, right? And then you can add more, a more descriptive, can actually add the index here, right? There we go. Find the node at that index. Aren't we glad that we put that into a function? Because now we can use that function. get element at index, right? At that index, and that returns a node, T. What should I call it? I'll just call it node, right? Now replace the element with the old element. So let me get the element first, or not int, but T, old value is equal to node.get element. And that's what I'm ultimately going to return there. So let me go ahead and put that in there as well, old value. Right. And now I need to replace the value. So node.set element to the old value. Right. That'd be really nice to have, right? Well, go ahead and give it to ourselves now. Now we have an argument for making that into a setter. Generally, you want to prefer immutable objects until you have a very good reason not to. And in this case, I have a very good reason not to anymore, because it's more convenient to have it and it's private, all right? And nobody can get access to my nodes to muck with them and set them to something that they shouldn't, right? Because it's all private. But now I have a good reason that internally I do want a setter for the element. So go ahead and generate that. There we go, done. Right. And now my linked list works. Write your own unit tests for that. I'm not going to go through that exercise yet again. But now, let's take the last one here. Remove element. Right. We're actually going to take the entire node out from the entire chain. Right. Let me come over here and let's look at a couple of corner cases here. Right. So if it's 10, 20, 30, and let's go 40 so that there are 4 things in here. And that goes to nothing. Suppose that we want to remove at index 2. What would that look like? Well, the first thing here's the head. Right? The first thing we would need to do is find that node right there. Right? At index, this is index 0, 1, and 2. So once we've found that node, we want to remove that node. How do we go about doing that? I need to sever this connection, and potentially I need to sever that connection, right? Question mark on that one. All I need to do is circumvent it. Right? Get rid of this connection and simply just point it over there. And also decrement the size, right? So all I need to do is make the previous node point to current nodes next. Right? And that's all I need to do. It's reduced down to finding these 2 nodes, and making sure that the previous one now points to that next one over there. Okay? Well, we've done this before, right? We did this up here when we had to insert something, right? Let me go ahead and get previous and next. Right, there we go. And I will cut and paste that code right here. By the way, what should I have done very first? Bounds check. Otherwise, I will get the previous, and I will call this current, right? Because that's a little bit better name, especially with the picture that I drew over here. This is the previous, this is the current that we want to remove, and then this is the next. That's current next, okay? So let me get all 3 of those actually. Node, T, current, or not current, but next, is equal to current.getNext. next. Now I've got all 3 of them and I can shuffle things around here, right? And all I'm going to do is say previous dot set next, or set next to next. That's it. There, right? All I've done is I've circumvented the current right here, right? And this dot size minus minus. Okay. Make sure that you're doing bounds checking appropriately if the index is less than 0 or the index is greater than or equal to this dot size. Then I'll throw a proper exception here. Throw new runtime exception, invalid index, and plus index. There. Okay. Is that all I need? Well, it's not compiling. What do I need to do? I need to return the old value. So return, what's the old value going to be? Current dot get element. That's it. What could go wrong here? Is there a corner? I mean, doing this in the middle, that seems like it should work. What's a corner case that we should consider here? Again, let me go ahead and give myself 10, 20, 30, and 40. Right? Removing something from the middle, that seems obvious. All you'd have to do is circumvent it. Removing 30, that's the same case. Circumvent it. What about removing 40? Think about the circumvention here. What you're doing is you're taking the previous and you're setting it equal to the next, which is exactly what you want. Right? So that's a corner case that probably doesn't need to be taken care of separately. Still needs to be tested, right? What's the other corner case that we should really, really think about here? What about when you're removing a head? Can you get the previous here in order to circumvent it over here to the second node, the old second node? Nope. There's a corner case that we need to consider. What does it look like, whiteboarding it up here, what does it look like to remove this element here? All we need to do is make sure that head is now pointing to the second node. Do we need to sever this connection right here? Not in Java. In Java, nothing, the garbage collector will see, okay, nothing refers to that, so I can go ahead and clean that up at my leisure. So if you're removing from the head, in other words, your index is 0, right? Then that's going to be a corner case here. If index is equal to 0, we need to handle that separately. Else, this works for all the other cases. And indent, there. We'll come back and clean up the code because obviously we're not going to want to decrement the size twice there. Right? So if the index is 0, all I need to do is set this dot head equal to this dot head dot next, get next, and that's it. And then this dot size minus minus. Okay. And then of course I need to return the old head, right? Return this dot head dot get element, except that I've already destroyed the old head, right? So let me go ahead and preserve it at least, or at least get the element. T old value is equal to this dot head dot get element, and then I can return that down below. Return the old value, right? Okay. All right. Let's take that and put it out, or actually, can I put it outside? Could I take those two instances and put it down here? The compiler is telling me I can't. Why? Because up here I've already returned. Up here I've already returned. So, yeah, sometimes it's okay to repeat yourself. Don't repeat yourself is a guideline, right? In this case, I have to, or I'd have to restructure everything. I would have to make a checkup here to see, are we removing the head? Okay, get that element. Otherwise, get that element. And then I would repeat the if-else-if condition down here for the rest of the stuff. Right? That would be a lot less clean. But there are ways that you can clean up this code, but so far this is looking pretty good. Let's do at least one test on this. Right? All right, I'm going to grab all of this code here. And instead of 42, since I'm not inserting anything anymore, let's call this remove elements. Remove element. And in fact, yeah, I'll call it remove elements. Right? So I'm going to add 10, 20, 30. All right? And I'll preserve those, the actual and expected. But now let's think about how we want to test this. All right? Let's go ahead and start by removing something from the middle. Right? So list.remove element at index, say, 1. Right? And that should return actual. That should return what? expected. 10, 20, 30. If I'm removing the guy in the middle, it should be 20. Right? And now let's assert that those are actually correct. Right? What else would we want to test here, though? Right? Yeah, you remove 20, but what about the rest of the list? The rest of the list should be now 10 and 30. So let's make sure that that's still correct. Right? Actual is equal to list.getElement at 0. And we're going to expect that that is 10 because 10 should still be there. And let's assert that that's in fact the case, that the expected is equal to the actual. And we should expect that 30 is still in there, but at what index at this point? What index should 30 be after we've removed 20? 30. Right. So what are the only things in there now? 10 and 20. So what's the second index? 1. Right? And so let me rename this element from middle. Right, there we go. And run that again. Now I should have 9 test cases in good code coverage here. Right? Okay, why didn't it do all of them? Come on. Sometimes it just needs a kick in the butt. Okay. Maybe because I've highlighted it? I don't know. You should find all 8 of them. Come on. There we go. No, there, now it's 9. Right? Probably because I was highlighting this, and so it can it's going to only run that one test or something. Right? What else should I do? I did from the middle. I should do from the beginning. I should do from the end. And I would cut and paste this code and then modify it to make sure that that happens. Just as a reminder that you have this other tool over here, right, where you've got code coverage. So let's see if we've taken care of all of the cases. This will run all the tests, but also it will highlight over here in my linked list, after it's done, there we go, all of the actual tests all of the code that was actually tested. Here we never tested the bounds check. That's why it's in red. Right? Did we ever test removing from the beginning? No, I only tested removing from the middle. So this code was tested, this green code right here, but this tells me, oh no, you need to write at least one more test case here for good code coverage. Right? That green stuff there, that was tested well. I never tested at all update elements, so I would need to do that. I never tested bounds checking, but otherwise everything else was well tested except for the bounds checks. Right? By the way, again, if you need to get rid of that because you want to, make it look nice again, just go ahead and hit the double X here to remove all of the color coding there. So you have a debugger, you have unit tests, you have a code coverage tool here that tells you what code is being tested and what code is not being tested. Right? Make sure that you're using that for all of your unit tests. Go back to your previous, where you were writing unit tests for your project. Run this code coverage here and see, is there something that I didn't test? Our requirements basically required you to test all the important stuff anyway, but maybe there's something that you didn't end up testing. All right, there's linked lists. Any questions? Otherwise, on Friday, what we'll do is we'll wrap up the linked lists and then move on to list-based data structures, including stacks and queues that will actually use lists from then on, that will actually use lists internally to them. Okay? All right, I'll see you on Friday.